Okay, so I promise you'll get better songs throughout the year. I've never even heard that song, but when I Googled something to do with water, I was trying to do something funny that applies to whatever I'm going to talk about. That was the first thing that came up. So we are talking about water, and we're dedicating an entire lesson to it. So obviously, you know it's important to us and every other living thing if we're talking about biology. Water really is the key substance on any planet that's going to support life. So when it says the biological medium on Earth, like all of our chemical reactions necessitate water. Not everything directly requires water, but water is going to have so many different characteristics of it that you have now experienced in the lab. And that's why you're listening to this after the fact, because I wanted you to look at them before and kind of decide for yourself how it worked before I actually told you how it works. So all living things require water more than any other substance. Most cells, like looking at our cells, are 75% water. It's why your body immediately tells you if you're dehydrated. If you ever feel thirsty, like if you feel right now that you need to go to the water fountain because you're really thirsty, it actually means that you're 2 levels beyond a hydration level that like where you should be, a target range where you should be. So if you're ever thirsty, you're well beyond where you should be from a hydration level. So whenever anybody's carrying around a water bottle, I always think it's really a good thing, more so than food, because we need water. You'll die far sooner. You can go 4 to 5 days maybe without water, depending on your initial hydration level. You can go 30 plus days without food. It's not going to be comfortable, but that just shows you how important water is. Not just, we think of water like, oh, I'm thirsty. Well, what does thirsty mean? It's your body telling you you need water for something in particular, and we're going to investigate all the reasons why. The abundance of water is just the main reason Earth versus Mars. When we look, or if you've seen movies like Interstellar, they're always looking for water. Yes, temperature, like surface temperature on the planet, but really they're looking for water because, again, water is important to all life. So hydrogen bonding is what this slide is about. You probably looked at this in chemistry last year. A polar molecule is when they have opposite charges. When a molecule is two elements put together, have different charges. So if you look at this, hydrogen, remember we're specifically talking about water right now, hydrogen ions are going to have a positive charge, and then oxygen, that central oxygen atom, is going to have a negative charge. It's actually 2 minus. That's why we need two hydrogens that attach to it. Because of that opposite charge, we call water a polar molecule. Polarity is going to be really important when we talk about solvents or solutions, so how water can dissolve other things in it. Things that are non-polar, like oil, if you've ever heard like oil and water don't mix, because of the opposite in polarity, water's polar, oil's non-polar, it's not going to mix together. One cannot dissolve the other, which is why you'll see kind of a neat little line forming between, like in a beaker, you'll see a neat line forming between the oil and water. Polarity, what we're concerned with is that polarity, that opposite in charge, allows these really weak hydrogen bonds from water molecule to water molecule. You saw this in your lab when you put droplets of water on the penny, that something had to happen in order for those molecules of water to kind of combine together. Even if you put two drips of water close to each other, that attraction, those weak bonds, are going to attract each other so that water molecules cohesively bind together. Since they're weak, they're not that hard to break apart. Like if you're in a pool and you jump in, those water molecules will splash up or off of each other because it's not bound together like other elements are in other compounds that you would have to chemically break them apart. Those hydrogen bonds are really weak, and yet they will kind of bring water molecules all together. So really, 4 emergent properties are important to life in general and important to how water works. So cohesive behavior, we don't need to define that right now. I would just absolutely know the slide, the four qualities of water. Ability to moderate temperature. This is really important to keep the surface temperature of Earth where it's at. Yes, we hear about global warming, but really water is responsible for absorbing a lot of that heat from the Earth's atmosphere. Expansion upon freezing, we'll see why that's important, and you saw some of it in the lab. And then versatility as a solvent. So again, you think of like salt water or Kool-Aid or a lot of the liquids that we would drink. It has the ability to, because of its polarity, absorb a lot of other compounds to make a solution. Cohesion is going to be hydrogen bonds that hold water molecules. I want you to put a star by water molecules. So this is water molecule to water molecule together. We're not talking about water molecule to some of the other things you saw in the lab, but the ability for water molecules to kind of hold together is called cohesion. This really helps when you are going up through, the small channels. You can see here through a plant, when those water molecules are fighting gravity, they don't have a circulatory system like a heart and blood vessels like we have. So the ability of water molecules to attract and pull each other up a plant is cohesion at its best. We require plants in order to breathe and for some of our diet. And so plants do not survive without cohesion, and therefore we don't survive without cohesion. Adhesion is going to be between water and some other, so in this case it's plant cell walls. You saw it in the lab between, when you looked at the meniscus, water adhesively binding to the walls of the graduated cylinder. You probably heard that term before, adhesion, like an adhesive Band-Aid. The Band-Aid, the sticky substance attaching to your skin. Well, the sticky substance, or what the Band-Aid is made of, is obviously not your skin, so we say it's adhesive, or adhesive tape is going to bind two substances that aren't necessarily alike together. So cohesion, water molecule to water molecule; adhesion, water molecule to something else. Surface tension, which this is another property of water. This is something that you saw with the paper clip. So surface tension is a measure of how hard it is to break the surface of a liquid. And that surface tension, because molecules of water cohesively bind together, is pretty strong. That's something that's lighter. Obviously, we're going to splash through a puddle or a pool of water, but something like an insect can absolutely move across water. Moderation of temperature, so water absorbs heat from warmer air and releases that stored heat to cooler air. So it's water, like if you think of water boiling, it's taking that heat from a source and then releasing it as steam into the air that's going to be less hot than that original source coming through in the form of fire. So water can absorb and release a ton of heat, and it's only going to allow a slight change in its own temperature. So again, it might be 104 degrees outside, and a pool, think of a pool. When it's 104, maybe your pool, and that's going to fluctuate day and night, but I'm saying your pool might be 90 degrees. Why does it not go all the way up to 104 degrees? Well, the pool is actually going to absorb some of the heat, and then it's also going to help cool the air, which we don't even think about. Maybe the temperature would have been 110 degrees outside, but all that water that's absorbing some of the heat and evaporating is cooling the surface of our planet. So it's really, really important as far as temperature regulation. It has a high specific heat. Specific heat is the heat of a substance, and the amount of heat lost must be absorbed or lost for 1 gram of that substance to change by 1 degree centimeter. So this builds into moderation of temperature. Water's high specific heat is going to minimize the temperature fluctuations, so we're not going to see huge swings in water. Even when it's, when it's 72 degrees outside at night right now, water does not go down to 72 degrees. It might go down a degree 2 or 3, and it might warm up a degree 2 or 3 during the day. 72, and then right now it's about 100 degrees during the middle of the day, but you're going to see water somewhere in between. So again, it has a high specific heat. that it takes a lot to raise the temperature of water 1 degree Celsius. So heat is absorbed when hydrogen bonds are broken from that heat, and heat is going to be released when hydrogen bonds form. So heat is released when water molecules are going to come together cohesively. Evaporation, all of this has to go, all of this is talking about the same thing, how water really cools our temperature. It's why on other planets you don't see water, and so you're going to see really cold temperatures or really hot temperatures, and that's why Earth is ideal for life. Evaporative cooling just means evaporation from a substance from a liquid to a gas. So again, think of sweating. Like your skin is going to release water droplets, and it's to cool the surface of your skin, so that water goes onto your forehead or onto your arms. It's going to suck up some of the heat. Again, your skin isn't going to be boiling, even if your surface temperature of your skin is really high. That sweat, the reason our body does it is the heat will be absorbed by the water, and then what's the next thing that happens? On a hot day, especially if you've ever been to a really dry climate with 0% humidity, maybe like Arizona. Dallas is relatively, some people think it's humid, some people think it's dry, but overall I would say it's on the drier side. And so what happens? It evaporates off of your skin, and what did it just do? It took some of the heat from your skin and put it into the air. So it's really good. Evaporative cooling is so important to engines and to humans and to really anything in the form of cooling. Heat of vaporization, you don't need to know that. Some of this is more advanced chemistry. I just want to, again, the theme of this is not these chemistry principles, but rather how important water is to everything, not just drinking and not just chemical reactions in our body, but everything in life. As a liquid evaporates, its remaining surface cools, a process called evaporative cooling, so I'm going to write sweating next to it. And it helps stabilize temperatures in organisms and bodies of water so that you're not going to see huge fluctuations in oceans. Yes, again, you will see fluctuations, but it's not going to swing back and forth, which then keeps the surface of the Earth, the land surface of the Earth, relatively cool and relatively stable. Insulation, so this is talking about ice. And ice floats in liquid water, which is completely different than other solids. If you put a rock in water right now, what happens? Well, it's going to sink. That's because the density of a rock is greater than that of water. What's crazy about ice is because if you look at this diagram right here, you see these neat, orderly, crystalline arrangements of water molecules that kind of hold the water molecules apart versus you're going to see shorter little bonds and a lot more energy. Those water molecules are going to be moving about, bouncing off of each other. And therefore, what you're going to see is a lower density. Lower density in ice, which is why it floats. And you might think like, why does that even matter? Well, it matters a lot. To think of the Earth is mostly covered by water, and if ice sunk, if it had a higher density than water, it would sink to the bottom, thus suffocating and really crushing any animal. But since it floats on the top surface and freezes, from the top surface of water going down, it kind of provides insulation for the animals underneath. Helps regulate the temperature of the water so that it doesn't freeze. So it provides like an insulatory barrier. And then it also, allows for all of those animals and plants underneath to still live until the water is a little bit warmer again. And so, again, it all has to do with the chemical structure and the orderly chemical structure of ice freezing. Actually, the most dense water is going to be at 4 degrees, so 4 degrees Celsius. So right before it freezes completely, its density is going to be greatest. So we actually want to hit freezing because those molecules are going to slow down a lot in the lower temperatures, causing kind of a weird density of the water, which is tough for organisms to live in. it's the solvent of light, and I'll explain what a solvent is. So a solution is just a liquid that is homogeneous. Homogeneous means, homo means the same, so same mixture of substances. It's uniform throughout the mixture of solid and liquid. A solvent is going to be the dissolving agent. So in most cases, and specifically in the unit we're in, water is going to be the solvent that we're talking about. It's going to be the substance present in greater amount, and that's always going to be a liquid. The solute is what is substance that's dissolved. So if we're talking about salt water, it would be the NaCl. If we're talking about Kool-Aid, it would be the sugar. It's going to be a solid that is dissolved in the solvent or the liquid. So a solute is always dissolved by the solvent, which is the liquid solution. Water is really versatile because of the polarity, because it, with those weak hydrogen bonds, and because of the positive and negative ends of those hydrogen and oxygen molecules, it works really well and can form these weak bonds with a lot of other substances. And aqueous, if you ever hear aqueous solution, is just one where the water is the actual solvent, which, to be honest, most solutions on Earth are going to be aqueous solutions. So water is an effective solvent because it readily forms those hydrogen bonds. And ionic, we'll get to ionic and covalent bonds next in chemistry as we lead into biomolecules. When an ionic compound is dissolved in water, each ion is going to be surrounded. So you can see the water is going to surround the solid, and then slowly but surely those solids are going to break free into the water, bounce off of each other, and form this uniform aqueous solution. This hydration shell kind of surrounds and fills in any crevices. Weak hydrogen bonds form because of the polarity. And now, slowly but surely, if you drop, think of it, if you drop like an Alka-Seltzer tab, slowly but surely those Alka-Seltzers, or like Airborne, if that means anything to you, it's going to fizz up. Well, what is fizzing? All of those particles kind of uniformly distributing, since water kind of encompasses the solid, and it'll eventually mix together and form an aqueous solution. A hydrophilic, I talk endlessly about this in anatomy. Hydrophilic, water loving, phile means love, is a substance that has an affinity for water, versus hydrophobic, water hating. And something in our body that's huge that uses both hydrophilic and hydrophobic at the same time as kind of a system of checks and balances is every cell in your body is going to use both hydrophilic and hydrophobic. Hydrophilic because we want water in our cells, hydrophobic because we don't want so much water in each cell that the cell would explode because of pressure. And so that's why we have a very specific amount of water that we need in the body, which is why we have our urinary system. So when we look at cell membranes, we'll talk a lot about hydrophilic and hydrophobic membranes that are going to attract and repel water. So most biochemical reactions occur in water. It's why we need water. Chemical reactions depend on collisions. Collision of molecules, you don't see it, you can see it under a microscope between the solute and solvent, but things are constantly bouncing off of each other, and that's also going to influence what phase of matter it is. Molecular mass is just the sum of all the masses of all the atoms in a molecule, and then, which you probably remember from chemistry, the number of molecules are measured in moles, 1 mole being 6.02 times 10 to the 23rd molecules. And then molarity, this is just a review. You are not going to be, other than this one, you're not going to be tested on it, and yet we want to do a better job in science of kind of bringing things together so that you remember what a mole is and molecules, and we're just trying to bring it together, that in looking at water or atoms or molecules and how all of that adds up into like the bigger picture into moles. Water is also a great buffer. So water, if you think of it, it's H2O. OH is going to be OH minus and H plus. This is going to be really basic. H plus ions are going to be really acidic, so put them together and they're going to be neutral. Water is very neutral. The water that you get out of a faucet is slightly acidic. You probably heard of acid rain before as well. Not acidic to the point where it hurts you, but if you've ever heard of like deionized water in chemistry or distilled water, that takes the ions out, so it'd be perfectly neutral. But water is a great buffer. It's going to resist changes in pH, which many chemical reactions occur at a very specific pH, a very specific acidity or basicity, and we're going to do a lab with this as well if you didn't cover this in chemistry. Acidic or basic, if 7 is neutral and water is neutral, certain things that are really acidic, like let's say lemon juice, might be a 2 versus sodium hydroxide, which is used in cleaning agents, might be a 10. And so water has the ability to keep things relatively, since the 80% of our, 75-80% of our body is water, it helps keep things relatively stable, not too acidic, not too basic, so that all chemical reactions can occur with the conditions that they need. An acid is any substance that is going to increase the hydrogen ion concentration, and a base is any substance that reduces, I should have put increases, or you can say for this one adds OH minus. The reason we can say reduces the H plus, because what do you think would happen if we add something with OH minus in? What is OH minus plus H plus? It's going to form water. So while it reduces the H plus concentration by adding the OH, because if you add OH, it's going to form water. Just like if we increase the H plus concentration, if we added equal amounts of OH minus, sodium or hydroxide rather, you would get water. The point being that water is a great buffer. The internal pH of most cells must remain pH 7, which is neutral. Buffers are substances then that are going to minimize changes. So they're going to minimize the swings in pH so that we can survive. Most buffers consist in an acid-base pair, and water is the perfect one. Base, OH minus, acid, H plus. It's the perfect combination of both really acidic, really basic, and they combine together to form water, and so they have the ability to donate either H plus ions or OH minus ions to anything that's added to our body to resist change. If you notice, why is water great? Yes, cohesion, like a lot of our cells need them to carry out reactions, but really water is great at resisting change, resisting pH change, resisting temperature change. That term that you're going to hear a lot throughout biology, homeostasis. We want to keep things relatively stable within our body at all times so that all of the chemical reactions that you've never even considered in your body can take place in the narrow ranges that they need. Acid precipitation then refers to anything below 5.6 on the scale. Remember, normal water is going to be 7, so that's significantly lower. Acid precipitation, because of what we do to the environment with exhaust from factories and from our cars, is going to alter. Think of it, where do we get water from? Well, it's going to be rain, replenishes the water supply. It's this cycle that goes from our Earth's surface and oceans and lakes up and swimming pools up into the air, and then precipitation is going to come back down. Well, with the addition of all these different chemicals that we put into the environment, acid rain is becoming a bigger and bigger deal, that it can mess with soil chemistry, and it can also damage life in lakes and streams, because that is where water